All right, so this is a video on lesson 6, day 1. So we're going to try to answer this investigative question. How can we explain the movement of air in a hail cloud? And you will need to write this question in your science journal. So that's the first page that you're going to copy down. As you can see, the question is up there. And then you've got a couple questions that you're going to write down, which we'll go through in the slide deck. So you can pause this video and take a moment to write those down. All right, then on a second page, or if you have room at the bottom of your first page, you can write down numbers 5 and 6. So take a moment, pause this, and write those 2 questions down. Okay, so these are the questions that you just wrote down in your notebook. And number 1 says, do larger parcels of air outside over the course of a day also end up doing what the balloon did in our classroom, and why? Friday, you whiteboarded this question basically and showed a model of air. So once the sunlight hits the ground and it heats up the ground, and the air hits that warmer ground, so those air particles hit the warm ground and by conduction get heated up. And once they get heated up, they move faster and the particles spread out more and the air expands and it becomes less dense. And then number 2, if you could observe the motion of the air in the clouds on a day when it hails, what do you predict you might see happening? So now think about the clouds and how clouds move, what happens to the motion of the air inside those clouds, and specifically when it hails. What might you see happening in those clouds? All right, number 3, take a look at this cumulonimbus cloud. This is a really big cloud that forms in our atmosphere. And what do you notice about this cloud? So take a moment and you can pause this video and observe, write down your observations about what you see with this cloud. What's the shape? What's the texture? What color is it? So everything that you notice about that cloud. All right, this question, how does a hail cloud compare to these other clouds? So here we have this cumulonimbus hail cloud, which you just described in question 3. And how does it compare to all of these other clouds? Okay, so take a moment and make observations in number 4. All right, taking a look at the elevation, notice that we go from 0 feet, so sea level, and we increase every 5,000 feet, all the way up to 30,000 feet. Answer number 5. What do we know about the temperature of the air at different heights of a cloud? Okay, so we did learn something about what happens to air temperature the higher up we go into the atmosphere. And then number 6, how might this be related to the formation of hail? So here's our cumulonimbus cloud, and this is where hail is formed. And at the bottom, this is the lower part of the cloud. Take a look at the elevation. What might the temperature be like down here? And then the higher up we go in the hail cloud, what might the temperature be? How can that relate to how hail might be formed in that cloud? Okay. All right. So this one, formation of a hail cloud, we're going to take a look at cumulonimbus clouds and how they form in a time-lapsed video. So I'll play the video and I'll be pausing the video at different points, and then we'll be marking on a handout where we see this hail cloud increase. So as we see it moving upward, we're going to kind of mark that with some arrows. How high does it go? We'll mark the height of the cloud with an X. And then do we see any downward movement in the cloud? So air moving down, and we'll mark that with arrows pointing down. So make sure you grab this handout if it's not been passed out to you yet. It's on the front table, so grab that handout so you can make your markings. And if you can get a red colored pencil, grab a red colored pencil to make your markings. And if you can see, we're going to be pausing at some of these different spots. Okay. Okay. All right. So once you get your handout, you can continue playing this video. Now that you have your handout, I'm going to click on the video. All right, and this is our cloud growth time-lapse video. Okay, I'm going to pause it here, and we can see this is only at about 7 seconds, and we can see some clouds kind of moving across this landscape. I grab the pen. I'm just going to start marking where I see growth of the cloud. Okay, I'm going to pause it here, and you can see that I made an arrow. We're only at about 24 seconds, but we did see a cloud rise up. Now that cloud isn't there anymore. Okay, so we'll kind of go back and see where did it go. Okay, we can kind of see when I pause it, and again, we're not very far into the video, but we can kind of see some downward movement happening with this cloud. So I'm going to get rid of the pen, kind of pause it again, and see if the cloud follows my arrows. Yep. Okay. All right, there it goes up, and there we see it going back down. All right, so I'm going to get rid of those arrows. I can erase those. Oh, maybe not. Oh, there we go. Doesn't seem to want to erase that arrow. Oh well. All right. Okay, we'll keep playing. All right, we can start to see more clouds forming. We can kind of see them going up and then back down, going up and then back down. All right, now we have one that's kind of building over there. Okay, so I'm going to draw some arrows. Oh, where did my mouse? Oh, where'd my arrows go? Okay, so there's my arrow, or my pen. All right, so we see a cloud rising, and there it is at the top. And we can kind of see it moving this way. We can see some downward movement of our clouds here. Okay, so what I'm going to do is I'm going to back up the video and pause it at some different spots and see if it follows this pattern. But you can see already, without the clouds even being there, I've got kind of this circular motion. So we'll back it up. All right, so here we are at about 43 seconds, which I think is right around the first picture of your dock. Okay, 45 seconds, we can see it rising. So on your dock, if you want to pause this and draw your arrows moving up at this point. Okay, at about 48 seconds, we can see that it's really right at the top there, and we can draw an arrow or an X marking the very top. Okay. In about 55 seconds, we can see some of this cloud movement coming back down, but we also see what's going on here, movement of the cloud going across. And we can see that the cloud is also rising. It's continuing to rise. And then we can also see it kind of goes back down right here. Okay, I'll just draw this down arrow. All right, we'll move it back and see how it follows those arrows. Yep, there it goes. We can see this cloud moving back down again, following that arrow. We can see this cloud going back up, and we can see it going back down. All right. Okay, so now that you have completed this, I think it's this stack right here. Yeah, nope. Okay, so now that you've completed this stack right here, so drawing our arrows, the X at the very top, and then towards the end, where did we see air moving down? Okay, so now what you're going to do is go back into Google Classroom, and you're going to open up this document right here. And these questions are there, and I'll kind of go through that doc with you, but you're going to work on this a little bit by yourself, and then we'll kind of come together as a class. I'll have you work on it once everybody's done with this video. I'll have everybody work on this together as a group, and then we'll also work on it as a class. Okay, so we have some data, and that's what this very first page is about, is some data. And here is an image. So it says question 1. We're going to try to explain the movement of air in a hailstorm cloud. So we have this question. This is an image of a cloud with data from Salem, Oregon during the summer around 4 p.m. So letter A says the date and the time of day. So Salem, it's on July 11th. It's in 2018. And the time of day is 4 p.m. And as you can see, we've got this hailstorm cloud, this cumulonimbus cloud that has formed. Letter B is data of the temperature at the ground and 4 feet above the ground for that day in Salem. So here we have a few different surfaces. The blacktop parking lot, in the sun, in the shade, in the sidewalk, and then on the sidewalk in the shade, so both the sun and the shade. And then the clearing in the brown forest. And you can see that the temperature right at the surface for all of these different surfaces. And then 4 feet above those surfaces, we can see that the temperature has slightly dropped. So this tells us that the air closest to the ground is the warmest, according to this data. Letter C says data from a weather balloon. So now higher up in the atmosphere, so 200 feet all the way to 40,000 feet, they took the temperature of the air. And we can see that it is decreasing the higher up we go. Okay, letter D is an image of a helium balloon. So remember the observational data that we collected with our helium balloon. When a helium balloon was heated, it expanded and it rose up, floated in the air for a while, and then it sunk back down. So all of that data is going to help us create a claim, what evidence from that data supports our claim, and then how does the evidence support our claim? So what is the reasoning? So let's take a look at the first one. We're going to make a claim that answers the question, what causes or what caused that upward movement of air in the cloud? So remember that cloud went up and then it went back down. And we know that that's what happened with our balloon too. So what can we put in these different areas? The sun. What does the sun do? What does this cause? Actually, there should be, and I'll change this in the doc, but there should be another place to write something after the word causes. So the sun, which causes something. So what does the sun cause to happen? What does that make the air do? Why does that affect the air? So what's going to happen to the air once that air is affected? So think about what we did in our model and what we did with our balloon. So you can go back to your page that you drew our balloon going up. We did this on Friday. What did we write down? So that claim is going to be very similar to what we wrote down with our two models from Friday. And then what evidence from the data supports the claim? So you're going to write what that data is from up top. So what data did you use here, okay, to support that claim that you just made? All right, part two. Okay, part two says make a claim that answers this question. Why does this type of cloud motion tend to happen more on sunny days? Okay, so on a sunny day, the temperature of the air near the ground, what does that depend on? So how hot the ground gets, what does that depend on? What happens on sunny days? Okay. And then what evidence from the data supports our claim? So we're going to go back up. What data up here talks about the temperature of the ground? Okay. So go back and read all of this data. Which one talks about the temperature of the ground? And you're going to list that data. Okay, so you're going to put that data right here. What data supports this claim? And then how does this data support the claim about what causes cloud motion on sunny days? So think about what the cloud does, why the cloud does that, and what evidence supports that claim. Okay, number 3, make a claim that answers this question. Why did the rising air in the cloud eventually stop rising and then start falling? So why does air fall? Okay, what happens to warm air? What does this cause air to do once it reaches the higher parts of the atmosphere? Why did it start falling? And then what evidence from the data above supports that claim? So again, which data up here talked about cold air the higher up you go in the atmosphere? And what happens to air once you get up to the higher atmosphere? It's going to start falling. Okay, and then why? Okay, so you're going to list that evidence here. And then how does this evidence support our claim about what caused the rising air to stop rising? Think about energy transfer, particle density. So you can go back to your models that we did on Friday. The class consensus model and our helium balloon model will help you. All right, question number 2. If you get to this part, there's a claim here. We've got big, tall clouds that produce hail, and they rarely occur in January in the northern hemisphere. So we're going to use radiation and land surface temperature data from NASA to support this claim, that hailstorms tend to occur more in the summer than in the winter in our northern hemisphere. So this is data right here that shows net radiation. So that's the amount of energy from sunlight that's absorbed by the surface. Okay, and this is in January. So here's the northern hemisphere. Take a look at the color. What does that mean? This is a key right here. We can see that the orange is, really more in the southern hemisphere. Of course, this is January. And the blue, which is going to indicate some cooler temperatures in our northern hemisphere. Okay, so actually this is more like April. Nope, January. Sorry, January. And then this is in July. Okay, so this is how it shifts in the northern hemisphere in July. So we can see that it flips. So could this help explain why hail forms mostly in the summer? And then our land surface temperatures. Oh, sorry, this was net radiation. So this is solar radiation, okay, not temperature. But that's going to affect temperature. So this is our data regarding temperature. So in January, we can see cooler and then warmer. And those correlate with less radiation in the northern hemisphere. We're going to get less temperatures, lower temperatures for our land, for northern hemisphere. And then we have more solar radiation, and that's going to give us warmer temperatures for the land. Okay, so what evidence from those two models here, from both of these diagrams there, what evidence from the data supports that claim, and then how does the evidence support the claim? Okay, so go ahead and type something in. You'll compare your answers with your group. We'll talk about it as a class. Just do the best you can.